Alright, hello everyone. Today, or now when you press the link, you're going to be looking at section 4.8, which is antiderivatives. So up until this point in the course, we've seen how to find derivatives using all kinds of rules, and we've also seen how to use derivatives. So how to find extreme values of functions, max and mins, how to sketch the function using, the first derivative and the second derivative, and how to evaluate limits, which are in indeterminate forms. In this section, we're actually going to begin to look at how to find the original function using its derivative. So we're going to be going backwards from differentiation. So if you remember, when we go backwards from one function to another, that concept is talking about inverses or inverse functions. And so this notion of an antiderivative is we're talking about actually the inverse of a derivative. So going backwards back to the original function. So we start off with a definition here. So a function f is called an antiderivative of f on an interval I if, and so this is going to be true if the derivative, so d by dx, of this capital F function is f of x. Okay, so if you take the derivative of this function and you get little f, then that original function, big F, is called our antiderivative. And so let's look at some examples. And in fact, I kind of did these examples in a weird way, so not many of them actually are antiderivatives. So example 1, determine if the following functions f of x are antiderivatives for little f. So I want to check this by taking the derivative of capital F and seeing if it equals little f. So if we take the derivative in example 1 of, yeah, that's pretty messy. Let's try this again. So if we take the derivative of our capital F function, so big F prime, we get that it's 6x. Well, our little f function is x cubed, so this does not equal our little f of x. So this is not an antiderivative. Okay, so for big F to be the antiderivative, when we take its derivative, we have to get a little f, which did not happen here. If we look at example 2, let's do the same method of checking. So we take the derivative of capital F, and capital F is 3x squared again, so its derivative is still 6x, but that's not equal to our x cubed plus 6. So this is also not an antiderivative. All right, moving on to example 3, we have capital F of x is this complicated looking function here. So let's start by rewriting big F of x because we want to take its derivative to check if it's an antiderivative. And so we want to rewrite this as negative 5 times x to the 4 plus 1 all to the power of minus 1. And so if I do this, I can actually avoid using a quotient rule and I can use a chain rule instead to find its derivative. So that's kind of nice. So now when we take its derivative, big F prime, well, the power, the exponent negative 1 is going to come down. So we'll have negative 5 times negative 1, which is positive 5. We're going to leave the inside the same, so x to the 4 plus 1. Now it's going to be all to the power of negative 2. And then the last part of the chain rule says we multiply by the derivative of the inside, which is 4x cubed. We don't even need to simplify. We can clearly see that this is not arctan of x squared. So this does not equal little f of x. So this is not an antiderivative. Okay, so then next we have example 4. I think this might actually be the only one that works. So when we go to take the derivative, big F prime of x, we get that it's 1 over 4. So we're taking the derivative of 1/4 e to the 4x. Well, 1/4 is just a constant, so it's just going to multiply by our derivative of e to the 4x. And then our rule for e to the 4x is we keep e to the 4x the same, and then we multiply it by the derivative of its exponent, which is 4. So now here we have a 1 over 4 and a 4, so these actually cancel out, leaving us just with e to the 4x, which is exactly our little f of x function. So here, it's actually our only example for these first few. This is an antiderivative, so we say yes. Big F of x is an antiderivative because when we take its derivative, we get little f of x. Okay, so then question 5, we want to take the derivative of big F of x again. And it's the same function, so its derivative is 1/4 e to the 4x times 4, which is of course just simplifies to e to the 4x. We just did that. But that's not equal to little f of x, which is e to the 4x minus 100. So we say, no, this is not an antiderivative. Okay, so that wasn't maybe the world's best examples, but basically your rule of thumb is if it's an antiderivative of a function, when you take its derivative, you get that original function. So something to notice and to think about, and maybe we can look at example 4 here. If I had added a constant to my capital F of x function, so if I had 1/4 e to the 4x plus, let's say, 7, something like that, then if I took its derivative, what would happen to that plus 7 is that it would just go to 0, right? The derivative of any constant is just going to be 0. So if I add a constant to this 1/4 e to the 4x to my capital F function, it doesn't actually impact whether or not it's an antiderivative, because when I take its derivative to check if it is, that constant just goes away. So this is something that I've made a note of. So if capital F of x is an antiderivative for little f of x, so that is if capital F prime is equal to little f, then capital F of x plus any constant is also going to be an antiderivative for little f of x. And that's just because when you take its derivative, that constant goes away. So we have a little definition here. So if f of x, capital F of x, is an antiderivative for little f of x, then we say the general antiderivative of little f of x is capital F plus c, where c is a constant. So if we're asking for a general antiderivative, we want you to add that extra constant to the end, because we know by adding a constant, we're actually not changing the fact that it's an antiderivative. So for our practice question here, we want to find the general antiderivative of f of x, which is equal to -5 cosine of x minus 8 sine x. So what you need to do here is you want to try to find a function whose derivative is that -5 cosine of x minus 8 sine of x. So let's write this down. So we want a function whose derivative is this little f of x. So we want the derivative to be -5 cosine of x minus 8 sine x. Okay, so let's do this term by term, piece by piece, and figure this out. So what function has derivative cosine of x? Well, we know that sine does, right? The derivative of sine x is cosine of x. So if I rewrite this as -5 sine x, I know that when I take the derivative of -5 sine x, I'm going to get -5 cosine x right back, which is what we want. Now for the next part, it's a little bit trickier. So it's -8 sine x. Well, I know that cosine of x has derivative minus sine x, right? So that actually means that if I put -8 cosine x here, that's not quite going to work, right? Because if you take the derivative of -8 cosine of x, you're going to get -8 times negative sine of x, which would turn into a +8 sine x. And we can see in our original function here, it's -8 sine x. So we actually want to have +8 cosine of x here. And because that derivative will already include the negative in it. So we don't need to put the negative into our antiderivative, because the derivative of that function is going to actually include the negative. So last step is to put our plus c, because we know if we add any constant to this, it's still going to have the same derivative. So that ends up being option D as our answer. Okay, so just like when we had derivative rules, there are antiderivative rules that are kind of quick. And so remember, we're trying to go backwards from a derivative. So we're trying to do the opposite. Or another way to think of it is we're trying to find a function that will have this as its derivative. So our first rule, if f of x is equal to k, where k is some constant, well, what function will have derivative k? It's going to be the function big F of x is equal to kx plus some constant c. right? And so if we want to justify this, we can say this is true since big F prime of x is just going to be that constant k. Okay, so let's do an example of this. So if we want to find the general antiderivative for the function negative 3 pi, well, negative 3 pi is just a constant, right? So capital F of x is just going to be negative 3 pi times x, because when we take the derivative, that x is going to turn into a 1, leaving us with the minus 3 pi. Then we can add any constant to that because it will still have the same derivative. And so what I like to do, especially at the beginning when you're new to antiderivatives, is you should check your answers. Okay, it's really easy to check if you're right if you're comfortable with taking derivatives. So the way that you check that you're right is you take the derivative, f prime of x, of your antiderivative. So if we take the derivative of negative 3 pi x plus a constant, we get just negative 3 pi, which is exactly equal to our original function little f of x, which is what we want. So that tells us that we found the correct antiderivative. So then example 2, or our second rule for antiderivatives, is the power rule. So this is analogous to the second rule that we saw for derivatives of functions. So remember, we want to do, so I'm going to write this down, we want to do the opposite of derivatives. So we want to do the opposite of derivatives. So let's think about what the power rule does when we're taking a derivative, and we'll try to do the opposite operations to that. So with a power rule, usually what we're doing is we're taking our exponent, n, and we're bringing it down in front to multiply it. And then we decrease our exponent by 1, right? If I was taking the derivative of that, I would have n times x to the n minus 1. So instead of decreasing our exponent by 1, we should actually increase our exponent by 1, right? We're doing the opposite. So instead of subtracting our exponent by 1, we add to our exponent by 1. And then the other thing to do that's opposite is that instead of multiplying by our exponent, we're going to divide by our exponent. So we actually get that capital F of x is equal to x to the power of n plus 1 divided by n plus 1 plus some sort of constant. So this is our general antiderivative for a power of x. So let's work through some examples to try to convince ourselves that this rule works. So the first example, let's find the general antiderivative of little f of x is equal to x. So capital F of x, using our power rule, well, this is x to the power of 1, so we want to increase our exponent by 1. So instead of being to the power of 1, it's now going to be to the power of 2. And then we want to divide by that same exponent. So we're going to divide by 2. So we have x squared over 2 plus 2. And let's check our answer. So to check our answer, we want to take the derivative of this function that we just found. And so the derivative of x squared over 2 is going to be 2x over 2. And the plus c part obviously is just going to be plus 0 because it's a constant. So the 2's are going to cancel. We're just left with little x, and that's equal to little f of x, which is exactly what we wanted. So our general antiderivative for a power of x works. Now in example 2, we want to find the general antiderivative of the function f of x is equal to 1 over x to the 4. Now if we remember, when we were taking derivatives of these types of functions, we first wanted to rewrite this as a power of x, right? Because we can't really apply the power rule to it without having it written in power form. So actually, before I take the antiderivative, I want to rewrite this as x to the negative 4. So I start by doing that, and now I'm ready to find my antiderivative using my power formula. So our power formula tells us we should increase our exponent by 1. So negative 4 plus 1, be careful, this is not negative 5, right? Because we're dealing with negative numbers. If you add 1 to negative 4, you get negative 3. And then you're going to divide by the same exponent, negative 3, plus a constant. So if you were looking to simplify this, you would have negative 1 over 3x cubed plus a constant. And you should check your answer and see that your derivative is in fact x to the negative 4, which it is. Example 3, we want to find the general antiderivative of this function f of x is equal to the square root of x plus 4x squared. Well, same idea with derivatives. We see a square root function. We also want to rewrite that as a power of x. So it's going to be x to the power of 1/2 plus 4x squared. Okay, so now using the power rule to find our capital F of x, so we want to increase our exponent by 1. So 1/2 plus 1 is now going to be to the power of 3/2, and we divide by that exact same exponent. So we're dividing by 3/2. For 4x squared, the 4 is a constant, so it's just going to multiply by our derivative, or sorry, our antiderivative of x squared, which is x cubed over 3, right? We increase the power by 1 and then divide by that same power. And then we don't want to forget our plus c. So simplifying this a little bit, let's think about this. So if we're dividing by 3/2, that's the same as multiplying by 2/3, right? We take the reciprocal, that 2 goes up into the top. So we have 2/3 x to the 3/2 plus 4/3 x cubed plus c. And we should check our answer. You'll see in my nice filled in notes, I check all of the time, but for this recording, I'll just check sometimes. So if I take the derivative, capital F prime of x, what would happen? I'd have 2/3 times, well, that exponent on the x to the 3/2 would come down as a 3/2. It would then become x to the power of 3/2 minus 1, which is just 1/2. Then we're going to have 4/3 times 3x squared, and then plus the derivative of c, which is just 0. So we actually have a lot of cancellation here. The 2's are going to cancel, the 3's are going to cancel, my 3's are going to cancel in my second term, and what I'm left with is little f of x, which is exactly what we wanted. So that means that we've taken the antiderivative correctly because we got our original function back. Now, number 3 is a little bit tricky. That's why it's its own rule. And again, it's analogous to what we did with the derivative. So when we were taking the derivative of x, we could use our power rule, but we didn't want to there. So it's the same sort of idea. So we don't actually want to use the power rule on this. So maybe I'm going to just make a note of that. So don't rewrite this. It's the one exception where I don't want you to rewrite it. So don't rewrite it. And instead, you want to think, okay, well, what function has derivative 1/x? So let's write this down. What function has derivative 1/x? And so hopefully ln x is coming to mind. So we know that the derivative of ln x is 1/x. So our antiderivative is ln x, but we actually have to be careful. So if I write just ln of x, the problem is that, okay, let's think about the domain for the function 1/x. What values of x are okay to plug in there? So pretty much any value except for x equals 0 is okay to plug into 1/x. So we can put positive x values and negative x values in there for x. We just cannot plug in x equals 0. But with ln x, we know that its domain is more strict than that. We also can't plug in 0, but we can't plug in negative numbers as well. And so in order for this antiderivative to be defined, we actually have to throw some absolute values on the x so that if there are negative x values, the ln function is still defined. So our antiderivative for capital F of x is ln of x, ln of the absolute value of x plus a constant. So let's work through a quick example of this. Let's find the general antiderivative for little f of x is equal to 3/x. We get that our general antiderivative, capital F prime, or sorry, not f prime, capital F of x, let's erase that. Okay, capital F of x is equal to 3 times ln of the absolute value of x plus a constant. So that's our antiderivative. Okay, next rule involves exponential function. So if our function is e to the power of some constant times x, what would its antiderivative be? Well, we want a function whose derivative is e to the kx. We know that e to the x is its own derivative, and if you have something like e to the power of 2x, you know that e to the power of 2x actually appears in its own derivative, right? So we need e to the power of kx to be part of the antiderivative because we know that the derivative of this is going to involve e to the kx. But let's think if we've actually got the right answer here. If I were to take the derivative of capital F of x right now, what would happen? I would have e to the power of kx, but the chain rule says I would also have times k there. So I would have this extra constant being multiplied by my antiderivative function. And we don't want that extra constant there. So if it's multiplied in the derivative, we want to divide by that constant in our antiderivative. So we're going to divide by that k and add a constant c. So let's actually just try to prove our answer here. So let's try to take the derivative of capital F of x the way that we've written it. So capital F prime of x would equal, well, if I ask you to find the derivative of e to the kx divided by k, and remember k is just some number, you'd say, okay, well, it's the derivative of e to the power of anything is just itself, so it's going to be e to the kx over k. But then because it's more than just x in the exponent, I need to apply the chain rule, and I need to multiply by the derivative of the exponent. So our derivative of k times x is just k, and of course my derivative of plus c is just plus 0. So then these k's cancel, and we're left with just e to the kx, which is our little f of x, which is exactly what we wanted. Okay, so let's work through some examples where we combine all of these rules. So example 1, we want to find the general antiderivative for the function x to the power of 4 plus e to the negative 4x. So when we're finding capital F of x, we want to find a function that has this as its derivative. So for x to the power of 4, we're going to apply the power rule, which is the exact opposite of the power rule for derivatives. So instead of being x to the power of 4, it now becomes x to the power of 5. And instead of bringing the exponent down and multiplying it, we actually divide by the exponent. So we have x to the power of 5 divided by 5 plus, for our e to the negative 4x, we're going to have e to the negative 4x again, but divided by negative 4. And plus a constant. So let's check our answer, which again, I think you should always check your answer when you're first starting with antiderivatives. So capital F prime of x, if we take the derivative of this function that we just wrote down, well, x to the power of 5 over 5, its derivative is going to be 5x to the power of 4, and it's over that 5, because remember, that 5 in the denominator is just a constant. So that's why I'm not using the quotient rule or anything. That's just a constant there. So I have 5x to the power of 4 over 5, plus I have this e to the negative 4x over negative 4 times negative 4. Again, I'm using that chain rule. So my 5's are going to cancel, my negative 4's are going to cancel, and this is exactly equal to little f of x, which is what we wanted. So example 2, we want to find the general antiderivative of this function here. So it's 4e to the x plus 2e cubed minus e to the 7x. So lots of exponential functions in it. So what would capital F of x be? Well, for 4e to the x, what function has derivative 4e to the x? Just 4e to the x. For 2e cubed, it's a little bit sneaky, right? 2e cubed is actually just a number. It's just a constant. So its antiderivative would be 2e cubed x, because when I take the derivative, that x is just going to turn into a 1, leaving me with the 2e cubed. Finally, for this e to the 7x, we're going to have e to the 7x, and then we're going to divide by the 7, because we know that when we take the derivative, we'll be multiplying by the 7, and so we want those 7's to eventually cancel out. So that's why we divide by the 7 here. Last but not least, we have plus a constant. So I'm not going to do it right here, but you should check the answer. So take the derivative of this capital F of x and make sure you get little f of x in return. So a couple more examples here. So we're on page 5 of the notes now. So we want to find the antiderivatives for the following functions. So I'm going to just put a little divider there. Okay, so our first function, we have f of x is equal to negative 2 over x plus secant squared 4x minus 10. So when we go to find our capital F of x, let's think about what happens here. Well, negative 2 over x, we know this is a logarithm. So this is negative 2 ln absolute value of x. That's my antiderivative for the negative 2 over x. For the secant squared of 4x, well, let's think. What function has derivative secant squared? So we know that its tan has derivative secant squared, so we need a tan of 4x. But let's just stop and think whether or not we're right here. So if I were to take the derivative of this capital F function, and I was taking the derivative specifically of the tan 4x part, what would happen? I'd have a chain rule, right? Because there's more than just x as the angle, there's 4x. So I would take the derivative of tan first, deal with the outside first, and that would be secant squared 4x, which is good. That's the part that we actually want. And then when I multiply by the derivative of the inside, I would be multiplying by a 4. But if we look up to our original function, it isn't multiplied by a 4. So we need to somehow get rid of that multiplication by 4, and we do this by dividing by 4, so that when we take the derivative, those 4's will cancel. The last part that we need is to deal with is this minus 10. So we want something that's going to have derivative minus 10, and we know that that's just minus 10x will have derivative minus 10. The final thing we add is the plus c, and that's again because if we take the derivative, that plus c goes away. So you should check this answer. It's in my fully filled in notes, the checking part, but I won't do it for this audio video because my writing is terrible, but you should be checking your answer to make sure you get back the original function. We'll do part C next, just for ease of scrolling. And so for part C, I have f of x is equal to minus cosine of 2x plus 5x to the power of 5 over x cubed minus pi squared. So I actually, to start, rewrote this function. So I rewrote this as a minus cosine of 2x, so I didn't change that part. But the 5 over x cubed, I rewrote as 5x to the power of negative 3. Sorry, this is messy. So we have 5x to the negative 3 minus pi squared. So coming up with capital F of x. Okay, so again, we want to find a function that has this guy as its derivative. So what function has cosine as its derivative? Sine. So we know that we should have a sine of 2x there. But let's think about taking the derivative of this and see how far off we are. So if I take the derivative of sine of 2x, what am I going to get? I'm going to get cosine of 2x times 2. Well, up above in my original function, I have minus cosine of 2x, and not times 2, right? There's no 2 constant there. So I need the negative sign, and I need to divide out by 2 to account for the chain rule part. So the antiderivative for this minus cosine of 2x is minus sine of 2x over 2. For the 5x to the power of negative 3, we want to apply the power rule, right? This is just some power of x. And so the power rule tells us we increase our exponent by a power of 1. So instead of being to the power of negative 3, it'll now be to the power of negative 2, and we just divide by the negative 2. And then last but not least, for the minus pi squared, we want the antiderivative of that. So what function has minus pi squared as its derivative? Minus pi squared x, because when we take the derivative of x, it just becomes a 1. And then again, last but not least, we got to put plus c there. Don't forget your plus c's. I once wrote an entire calculus exam and I forgot plus c on every single answer, and it was not great in terms of losing marks. So don't forget your plus c's. Okay, moving on to B, we want to find the antiderivative of 2 times the cube root of x minus e to the 7x plus 6 to the power of x. So this is a bit of a tricky one. The first thing that sort of strikes my eye is that we have a cube root of x. So it'd be better if we rewrote this as a power of x. So 2x to the 1/3 minus e to the 7x plus 6 to the power of x. So capital F of x, finding our antiderivative now, we can do it term by term, piece by piece. So the antiderivative for our first term, this 2x to the 1/3, we can use our power rule. And our power rule tells us we increase the exponent by 1, so, oops, that's wrong. So we want 1/3 plus 1, which is going to be 4/3, and we divide by the same exponent, so divided by 4/3. For e to the negative 7x, we have e to the negative negative e to the 7x, we have e to the 7x divided by 7. And then this plus 6 to the x is a little bit tricky. So let's think about the derivative of 6 to the power of x. So if you remember, hopefully you remember the derivative of this. The derivative of 6 to the power of x is 6 to the power of x times ln x. So it's kind of like e to the x's derivative. It appears in its own derivative, and then it's just multiplied by ln of the base. So if I put plus 6 to the power of x here, let's see how close I am. If I were to take the derivative of this capital F function, this 6 to the power of x here, its derivative would be 6 to the power of x, which I want, times ln 6, which I don't want. So we need to get rid of the ln 6, which is just a constant, and it's being multiplied in the derivative. So the way that we do that in the antiderivative is we divide by ln 6. Last but not least, plus c, and again, you should be checking your answers here, and you can double check once you check your answers on your own notes, double check with the posted notes that I posted to Course Bases, and make sure that you're checking the same way that I'm checking. But when you take the derivative of this capital F function, you should be getting that small f function back in return. Okay, last example before we move into some new notation. So we have little f of x is equal to secant of 3x times tan of 3x minus 4 to the power of 9x. Okay, so it's a little bit tricky, but we can work this out. So capital F of x, let's start with the secant tan portion. So we need to find a function whose derivative is secant 3x times tan of 3x. And so you're probably thinking of secant, and that would be right. So we know that the derivative of secant of 3x is equal to secant 3x tan 3x, but there's a chain rule in there as well, right? It's not just equal to secant 3x tan of 3x, it's equal to that times 3, because the last thing that we do is we take the derivative of the inside, which is 3. So we look up at our original function and we see that this secant tan is not multiplied by a 3 here. So in our antiderivative, we need to get rid of that 3 by dividing by it. So the first part of our antiderivative is secant of 3x divided by 3. Now for the second part of our antiderivative, this is a little bit tricky. So for 4 to the 9x, well, let's just start by putting 4 to the 9x down and see how close we are. So if I were to take the derivative of 4 to the 9x, what would happen? I would get itself back, right? I would get 4 to the 9x times ln of the base, so times ln 4. And then because it's 9x in the exponent and not just x in the exponent, I would have a further chain rule, which would be the derivative of the exponent. So the derivative of 9x, which is just 9. So to reiterate, if I were to take the derivative of 4 to the 9x, I would get 4 to the 9x times ln 4 times 9. Well, looking up at our original function, we have the 4 to the 9x, but we don't have the ln 4 and we don't have the 9. But luckily, both of those values are just constants, so we can just divide out by the same constants, so the 9 and the ln 4. We divide out by that and you check your answer, you'll see that you're left with just the 4 to the 9x when you take the derivative. Okay, so we're speeding right along here to page 6. So we're going to introduce some new notation for antiderivatives. The process is still going to be the same, but we're going to be using some new symbols. So consider a function little f of x, which has a general antiderivative capital F of x plus c. we can represent the antiderivative of little f with respect to x by something called the indefinite integral of f with respect to x. And so this is denoted by the integral of little f of x dx, and this is equal to capital F of x plus c. And so I just want to make a note here. This integral symbol, so this thing that kind of looks like a long S or like a little bit like a snake, that symbol and the dx, they're a package deal. So this and dx come and go together. So either both of those symbols are there or neither of them are there. You should never just have one of those symbols there. So let's work through a couple examples, and remember, we're not actually doing anything different. So if I say to find the indefinite integral, I'm just asking you to find the antiderivative. So if I want to find this indefinite integral in our example here, I'm finding the antiderivative of x to the power of 4. That's not a very good 4. The antiderivative of x to the power of 4 plus the square root of x, which I'm going to rewrite as x to the 1/2, minus 5, maybe I'll throw some brackets around this, dx. Okay, so once I find my antiderivative, this is when I want to drop the integral sign and the dx sign. So maybe let's just make a note. So once you find the antiderivative, which I'm sure that's not going to look very legible when I write it down. So once you find the antiderivative, you drop the integral and dx symbol. Okay. So let's do this term by term. So the antiderivative of x to the power 4 is going to be the power rule. So increase your exponent by 1. So it's x to the power 5 divided by 5. For x to the 1/2, same thing, power rule. So we increase the exponent by 1, which is x to the 3/2, and we divide by the exponent, which is 3/2. Last but not least, we have the antiderivative of minus 5, and that's just going to be minus 5x, right? We're trying to find a function whose derivative is minus 5, so it's going to be minus 5x. And then plus c. So just a little bit of simplifying here, because I don't like dividing by a fraction. So we have x to the 5 over 5 plus 2 over 3 x to the 3/2 minus 5x plus c. And again, because I'm writing with the stylus, my writing is super big. It looks like I'm in kindergarten. And so I don't have enough space to do the checking of the answer. But I did do this in my written notes, and you should be doing it for every single antiderivative question until you're very comfortable. Okay, so for this practice question, I want us to try to find the antiderivative for 4 over x plus 1 plus 1 over 1 plus x squared. So let's start off with the 4 over x plus 1. We want to think of a function that has this guy as its derivative. And so you can see the sort of structure of a 1 over x plus 1 there, and then multiplied by 4. And so the 1 over something should be reminding you of logarithms, right? And so ln of the absolute value of x plus 1 needs to be in our antiderivative. So that eliminates a and c because there's no absolute value symbol there. So we're between options b, d, and e. Now let's look at option b for a second here. It's saying that the second antiderivative, the one for 1 over 1 plus x squared, is ln of 1 plus x squared. So let's think about why that is actually wrong, because it isn't correct. So if I were to take the derivative of ln of 1 plus x squared, what would happen? Sure enough, I would have the 1 over 1 plus x squared, which is something that I want, but the chain rule says I would also have to multiply that by 2x. So the derivative of this guy here, maybe I'll just write this. So if I take the derivative, d by dx, of ln of 1 plus x squared, you have to remember the chain rule. You get 1 over 1 plus x squared, but you get times 2x. And you cannot just divide out by a variable to correct your antiderivative. So even if I put ln of 1 plus x squared divided by 2x, that would still be wrong, because imagine what happens when you take the derivative of that. You would have to use the quotient rule. So you can't, when we had a constant above and we wanted to get rid of the constant, we just divided out by the constant. It was pretty simple. But if you have an extra variable there, like this 2x, this just means this is not the antiderivative. There's no simple way to fix this. In fact, we're going to be learning a technique in our last section in this course, which will help us deal with these sort of scenarios. So we know that ln of 1 plus x squared is not the antiderivative for 1 over 1 plus x squared, because the derivative of this ln has an extra 2x there that we don't want. So instead we have to think, okay, well, is there any function that we know of that has derivative 1 over 1 plus x squared? And hopefully you guys recognize this as an arctan. So this is actually arctan of x's derivative, so our answer is E. Okay, and that one, there's not really any work involved in it. It's just it's a derivative that you need to know. So the derivative of arctan is 1 over 1 plus x squared, so we know the antiderivative of 1 over 1 plus x squared is arctan. Okay, so the last thing we're going to do in this section is, so starting on page 7, is something called initial value problems. So let's sort of read the summary here together. We have seen that we use the indefinite integral, or antiderivative, to go from the derivative function to a general version of the original function. So when we've been finding the antiderivative, we've always had this plus c there, and we didn't know what that c was, right? We just said it could be any constant. So we're now going to see a way to find the specific original function by solving for that constant c. So in our first example, we're going to use velocity and the position function, because we know that the velocity is the derivative of our position function. So example 1, the velocity of a moving body is given by v of t is equal to 9.8 t minus 3. We want to find the body's position function s of t, given that s at 0 is 5. So let's start off by writing down the relationship that we know between the position function and the velocity function. So we know that the derivative of position is velocity, right? So if we want to find the original function, we need to take the antiderivative of velocity, right? So when we wanted to take the derivative, if we had the position function and we wanted velocity, we would take the derivative. If we have velocity and we want the position function, so this is the opposite scenario, we have to go backwards. So we're taking the antiderivative, right? We're going from the derivative function of the velocity back to the original function, which is the position function. So this is why we're using an antiderivative. So s of t is going to be the antiderivative of this 9.8 t minus 3 dt. So let's think what that's going to be. Well, this 9.8 is just a constant, so it's going to stay in front. And then the t, we're going to apply the power rule. So it's going to be t to the power of 2 divided by 2. Minus 3 becomes minus 3t, because the derivative of minus 3t is just minus 3. And then we need plus some arbitrary constant. So we end up, if we do the division of 9.8 divided by 2, we get 4.9 t squared minus 3t plus c. So the whole point of these problems, initial value problems, is that we've been given more information, right? We don't just know the derivative. We also know a point on the original function. We know that s of 0 is equal to 5. And so if we use the fact that s of 0 is equal to 5, we're actually going to be able to solve for our constant c. So keep in mind, 0 is my value of t, and 5 is like what would normally be your y value, but in this case it's your s value. So you have 5 is equal to 4.9 times 0 squared minus 3 times 0 plus c. So solving for c, you actually get that c is the constant 5. So that means if I actually wanted the specific position function that satisfies that derivative and that initial point, we get that s of t is equal to 4.9 t squared minus 3t plus 5. And that would be our final answer. So working through the next example then, it's a similar idea. We wanted to determine the original function evaluated at x equals 1. We know its derivative and we know a point on the original function. So again, we're in the scenario where we have the derivative, but we want to move backwards. We want to go back to the original function. And so this is going to use antiderivatives again, because those are going to take us from the derivative back to the original. So we know that the original function f of x is going to be the antiderivative of f prime of x. So this is going to be the integral of negative x squared plus 8 dx. And notice I've always got that integral symbol and the dx together, and they go away at the same time. So when we take the antiderivative of this, I no longer need my integral symbol or my dx. So minus x squared's antiderivative is minus x. So I increase my power by 1, raised to the power of 3, and divide by that same exponent, so divided by 3. Plus, for 8's antiderivative, I want a function that has derivative 8, which is going to be the function 8x. So 8x is the next part, and then plus an arbitrary constant c. So we want to use all of the information we have. So we want to use the fact that that f of negative 1 is equal to 3. So we're going to use, that f of negative 1 equals 3. And this is going to allow us to solve for our specific constant. So using that, we get that 3 is our y value and negative 1 is our x value. So we have negative 1 cubed divided by 3. You can tell I'm getting a bit tired here. Okay, plus 8 times negative 1 plus c. And so solving all of this, we end up getting that our constant c is equal to 32 over 3. So I definitely used my fraction button on my calculator to do this. So then what can I say? Well, I actually know that my f of x function is going to equal negative x to the power of 3 over 3 plus 8x. And my c I now actually know is 32 over 3. So I've actually solved for my specific c. But the question itself isn't asking for f of x, it's asking us to determine f of 1. And so I have to evaluate my function at x equals 1. So that's going to be negative 1/3 plus 8 plus 32 over 3. And assuming I use my calculator correctly, which is always a bit of an assumption, I got 55 over 3 as my answer. So this is our process for an initial value problem. So you have an initial value problem when you're given a derivative and you're trying to go backwards to an original function, but on top of having the derivative, you also have a point on that function. So that's what makes it an initial value problem. So we have one more example to work through, and this is a harder one because we're actually going to go from the second derivative to the original function. So we actually have to do antiderivatives 2 times. So just like when you want to go from the original function to the second derivative, you have to first go through the first derivative and then go to the second derivative. It's the same idea here. If we start with the second derivative and we'd like to go to the original function, we first have to go backwards to the first derivative, and then from the first derivative we can go backwards again to the original function. So same sort of idea, there's no sort of shortcut here. Oh, sorry, I said this was the last example. There's last page, 2 more examples. So we start off with the second derivative. So I can't jump all the way to the original function. I have to go from the second derivative just to the original function. So, to the first derivative. So I'm going to say we know, help if I have my pen turned on. So we know that g prime of x is equal to the antiderivative of our second derivative, right? If I want to go backwards by one derivative, I take the antiderivative. And so we want to take the antiderivative of this 3 over 8x dx. Okay, well, let's apply our power rule to this. So 3 over 8, the antiderivative of x is x to the power of 2 divided by 2, and then we have to add a constant to that. So let's simplify this a little bit. We get 3 over 16, because 8 times 2, on the bottom there we have 16. So 3 over 16 x squared plus a constant c. And at this stage, we actually could solve for c because we know a point on this g prime function. We know that g prime of 4 is equal to 3. So we can use the fact that g prime of 4 equals 3, and that's going to help us solve for this constant right away. So we have that 3 is equal to 3 over 16, I'm plugging 4 in for x, plus c. And so I end up with, let's see what happens here. I have 3 plus c is equal to 3, so that actually solves that c is equal to 0. So that actually tells me that that constant was actually 0. So g prime of x is just 3 over 16 x squared. I don't need a plus c because we've solved that that constant is in fact 0. So the next thing that we want to do is go from the first derivative to the original function. So we're going to use antiderivatives again. So now we know that our original function g of x can be found by taking the antiderivative of g prime of x. Sorry, that's quite messy. So g prime of x dx. So we're taking the antiderivative of this 3 over 16 x squared dx. Okay, so let's try to do this. So we have the 3 over 16 still. For the antiderivative of x squared, the exponent's going to go up by 1, and we divide by the same exponent. And then we want to add a constant to it. I'm going to put plus k because it's just good practice not to use the same variable twice in the same question for different meanings. So I'm going to write plus k there instead of plus c, but you could put maybe plus c2 or something like that, and that would be the same. So simplifying this a little bit, the 3's are going to cancel, and so I have that my original function is equal to 1 over 16 x cubed plus some constant k. But we do actually have some more information, right? We have some information about the original function. We know that g of 1 is equal to 4. And so now that we have what the original function is, we can use this information. So I couldn't have used this earlier when I found g prime of x because this is not information about g prime, right? This is information about g. It tells us that g of 1 is equal to 4. So plugging this in, I have that 4 is equal to 1 over 16 times 1 to the power of 3 plus k. And so I end up getting that k, sorry, I'm just going to move my screen a little bit. Oh, I have all this space, how luxurious. I end up getting that k is equal to 63 over 16. So my final answer for what g of x is that it's 1 over 16 x cubed plus my k value, which we found to be 63 over 16. Okay, so that was an initial value problem. That's about as hard as it gets, right? Where you have two steps, where you have the original, you're going from the second derivative to the first derivative, and then from the first derivative to the original function. So two antiderivatives in there. So the last thing, the practice question, and maybe you want to pause and try to do it on your own. So I'm giving you the derivative of this function here. So dr by d theta is cosine of pi theta, and I want you to find r of 1 over 6, given the fact that r of 0 is equal to 1. So I'm trying to find my original function r of theta, and I know the derivative function. So I need to use antiderivatives to travel backwards. So my r of theta is equal to the antiderivative of cosine of pi theta d theta. Okay, so this is cos theta, cos of pi theta is my derivative function. If I take the antiderivative of it, that will get me back to my original function. So for cos of pi theta, we want to find a function that has that as its derivative. So we know sine has to be involved somehow. So I'm going to just write a sine of pi theta there, and then I usually write the parts that I know, and then I think of the derivative and see how far off I am. So, okay, I know there has to be a sine of pi theta there. What would happen if I took its derivative right now? I would get the derivative of sine is cosine, so I'd have cosine of pi theta. But then for the chain rule, it would then be multiplied by pi. So I don't want it to be multiplied by pi, which means I need to divide out by pi and add a constant. So my antiderivative is sine of pi theta divided by pi plus a constant. Now we know more information. We actually know that r of 0 is equal to 1. So we can use this information, plugging it into our function. So we have 1 is equal to sine of 0 over pi plus c, which actually tells us that the constant c is in fact 1. So if I want to determine, so r of theta is going to be sine pi theta divided by pi and plus my constant value of 1. So the last thing I need to do is to determine r of 1 over 6. So I'm plugging in theta equals 1 over 6. That's going to be sine of pi over 6 divided by pi plus 1. You can remember your special triangle for this. So it's the 1 root 3 2 triangle. And this is not very clear, but this is angle pi over 6 here. And so if I do sine, that's going to be opposite over hypotenuse. So what are we going to have? So we're going to have 1 over 2 pi plus 1. So our answer, I actually have an error on the answer I posted on CourseBasis. So the answer should be A, 1 over 2 pi plus 1. Okay, and so that is it for this lecture. And now that I'm realizing I posted some false information on CourseBasis, I will go fix that now. And yeah, so moving forward, we're actually going to start talking more about antiderivatives and integrals. And we'll talk about the meaning behind them. So we actually can tie this into area underneath functions. So that's where we're going to be going moving forward in the course. And we'll finish off with just some techniques of finding the antiderivative when the functions get a little bit more complicated. All right, so that is it for section 4.8. Thanks so much for listening.